Well, I guess it's time to start. Welcome back, everyone. So our plans for the rest of the course are, we have 4 normal weeks of classes to cover. Our exam week is going to be a week after the next, so it'll be midway through April. Then on the April 22nd, that will be our closed week. And so for us, closed week means there'll be no quizzes because we don't have quizzes, no exams. Instead, we're going to have a couple sections that will cover new material, and then we'll spend about half of the week reviewing for the final exam. And finals week will be held on Monday. Ours is probably 8 to 10 p.m. in this room. But as soon as I have the finalized information, I'll both post it here and make an announcement to class. But that's where we're at so far. Any questions, folks? Okay, I guess I have a couple questions. One question is what's going on with my head. So just to get out of the way, I had a mole removed. They did a report on it. It's benign, so I don't have cancer. So I'll be around for the rest of the semester. And they had to cauterize it, so I'm going to look like this for a couple weeks. That's just part of life. I'm glad I remembered to tell you folks. I forgot to tell the last class. So they're probably wondering what's happening, and that's okay. But other announcement is we covered 2 new tests last class, the comparison test and the limit comparison test. Any questions about it before we go to new material? Okay, and another thing that we did was we looked at essentially a worksheet at the end of section 11.4. And thanks for mentioning, Mike, the solutions were not up as a PDF. So there's another PDF with answers. So if you want to practice the test that we had up to the end of class on Thursday of last week, then this problem here would be a decent worksheet type question. But we're going to have new tests every day, it looks like. So that kind of worksheet would get longer and longer. And I'll look for more material to post as well, in case people found that to be helpful. But let's go back to where we're at so far. Assignment number 7 is going to be, 8, due the 28th of this week. If you have questions you'd like to discuss at the start of class, I'm always very happy to go over them. And assignment number 9 is slowly being built. It'll be due the 4th of April. So should we start then? Okay, so that's the end of the announcements. Let's discuss first what we mean by alternating series, but we should also discuss why we need to get more tests. So the reason we're throwing more tests at the picture are our last 2 tests, the comparison test and the limit comparison test. It does have some problems, and it's whenever we assume things have to be positive. To work with these tests, the terms of the sequence and series all have to be positive. And that's the same situation with the integral test. For everything else, we can have positive and negative terms, so that's why we need more tests. The alternating series test will get away from this strict need of positivity in the sequence and series. But it's still not quite where we want to be. We're going to get to alternating next. So let's start by saying exactly what we mean by an alternating series. So we can say the series, summation as n goes from 1 to infinity of a sub n, is alternating that's the thing we'd like to define if the nth term, a sub n, can be written in the form a sub n is equal to -1 to the power of n times b sub n. So that's what we mean by alternating. It's really this portion right here. We're going to insist that b sub n is always positive. So when we use that in the series will involve always positive terms coming from the b sub n portion. When we multiply it by -1 to the power of n, this power is going to change with the index. So this whole thing is going to alternate from being a positive term into a negative term repeatedly. So here, well, let's say where b sub n is bigger than or equal to 0 for all n. So if that's the case, we have an alternating series. Still, we have a problem because our tests, sure, they require positive terms. Now we have a new test that we're going to do, the alternating series test, that can account for negatives only if the series is alternating. If the series is still not alternating, then we cannot use the test. So let's look at just some quick further examples beyond the definition. Any questions first with the definition? Okay, so alternating essentially means there is this portion in the series. If you have that, then it's definitely alternating. So a couple of quick examples. We're not going to test these, we're just trying to decide if it fits the format of an alternating series. So let's do some quick examples. And here we'll add it to the table if it's alternating. In this column, we'll put in the series. So if we have a series that looks like this, summation as n goes from 1 to infinity of, let's let this be, say, negative 1 to the power of n, 3 to the power of n, divide by 2n plus 1 factorial, then we would say that this is alternating, really not because of anything except for this. It's all that allows the entire series to alternate. So we can say for this one, yes, this is alternating. Does that make sense with that row on the table? Okay, kind of a quick table. Let's add another one. Let's go summation as n goes from 0 to infinity. It's kind of weird that it starts off at 0, but it could really start with whatever index we'd like for the lower end. And let's let this be, say, sine of n pi divided by n plus 3. This one's kind of nasty, because on the onset, when I look at that, I would say, no, it's not alternating. But it turns out, yes, this is alternating, even though it doesn't have this explicit form. Do folks see why it has to be alternating? Yeah, the sine function with n pi is going to continually oscillate. When n is 0, this will be sine 0. And so sine of 0 will be 0. But when we put in 1, we'll have sine of pi, which will give us a 0. When we put in 3, we'll have 3 pi, which will give us 0. Oh, hang on, that's not alternating at all, is it? Well, we're close. Let's change one little thing. How about cosine? That's a little bit better. If we put in 1 for there, or 0 for there, that'll be cosine of 0 pi. 0 times pi, cosine 0 would be 1. If we put in 1, it'll be cosine pi, which is negative 1. If we put in 3, it'll be cosine 3 pi, which is back to negative 1. So it looks like this one would be alternating. Does that make sense for that one? What the problem was with the sine of n pi? Okay, so sine of n pi, we're always going to get 0, but cosine n pi, we might as well make that look a little bit prettier. This is going to alternate between positive 1 and negative 1 forever. We're essentially just going on the unit circle, starting here when n is 0 for a positive 1, rotating here for a negative 1 when n is 1, then back to 0, which will give us a positive 1 for cosine when n is 2, and so on. So we can say, yes, since cosine n pi is really negative 1 to the power of n itself. Does that make sense with that one? Doesn't work with sine, but we could do the right phase shift to make that happen. Instead, let's go off to the next one. Let's let this one be, how about summation as n goes from 0 to infinity. Now let's let this one be something like, how about sine of, let's go with pi divided by n, divided by n minus 4. Okay, so that's, once again, another nice series. It doesn't have the negative 1 to the power of n, so we might say it's not alternating. But, or excuse me, it doesn't have cosine n pi, which is negative 1 to the power of n. But we should be suspicious. How about sine pi divided by n? Would that one alternate or not alternate? Oh, we should probably start this somewhere, which doesn't cause a division by 0. Let's start it at 1. So when n is 1, we would be at sine pi. We would get, for the very first term, sine of pi is 0, so we get a 0 for our first term. Then when we let the index n go to 2, with n is 2, we would have sine of pi divided by 2, so we're now up here, divide by 2 minus 4. So that would all together be plus a 1 divided by negative 2. So that one would be negative. So it is, I guess, somewhat alternating. We started with 0, which is neither positive or negative. The next term is negative. But now when n goes to 3, this is the value for n is 2, n is 1. When n goes to 3, we're going to have sine pi divided by 3, which puts us up here. And that's a positive root 3 divided by 2. So we have something positive when n is 3. Root 3 divided by 2, by putting 3 down in this place for sign. Then if we put 3 down below, it's a negative 1. So we've gone from negative to negative. And it doesn't matter what we have next. The next term could be positive or negative. But as soon as we match up the sign, we didn't alternate, which means the whole series has been ruined. If it eventually alternates, we may be able to use that test. But it looks like we're going to possibly switch to a sign that's positive and stay positive forever for the rest of the series. In other words, the terms for the numerator are going to essentially look like this. They're always going to come out giving us something positive. So this would be the example of something that is from here to here, not alternating. An explanation for this one was just show the terms of the series. The first 3 terms look like this. I'll go plus dot dot dot. But for the explanation was from term 2 to term 3, already it cannot be an alternating series. Which is important because it tells us we cannot use the alternating series test. Any questions so far about the alternating series we've looked at and the non-alternating one? Okay, so let's go to the alternating series test and see what it says. So this is the alternating series test, and it's our only test for today, so we're not going to try to cram several in one day. The alternating series test says if summation as n goes from 1 to infinity, let's write it in this form, negative 1 to the n times b to the power of n. If this is an alternating series, and 2 things have to hold for this alternating series, and if part 1, b sub n, as n goes from 1 to infinity, is decreasing for the first condition, and condition 2 is that the limit as n goes to infinity of b sub n is exactly 0, then that's all we need for convergence. In an alternating series, as soon as those 2 things hold, we have convergence, and only convergence, which is a downside to this test. All right, if conditions 1 and 2 hold, then the summation as n goes from 1 to infinity of negative 1 to the power of n, b sub n, our alternating series, it converges. So that's the entire test. It's a great test because really the entire battle is to determine if you really have an alternating series. If the series really does alternate and is both decreasing and is limit 0, then well, those are quick things to test. You can conclude the series would converge. What's missing is there is no test for divergence using this alternating series. So if we have an alternating series that we suspect diverges, then it's possibly because this does not hold. We would use the test for divergence possibly as the next go-to. Any questions so far about the test? Okay, let's try out a couple problems using this as a test. The instructions will say simply, which we're kind of used to at this point, test the series for convergence or divergence. Okay, that is a good prototypical problem to start with. Let's test n equals 1 to infinity, negative 1 to the power of n, divide by n. So that'll be our first series coming back from the break. If it was just ordinary 1 over n, as n goes from 1 to infinity, what would happen to that series? Or what is the name of that series itself? This one over here. Yeah, so that's our harmonic series, which is also a p-series, but we do know it diverges. P is 1 in this case. So this is the divergent harmonic series. We give it a name because it comes up quite a lot in this chapter. So being able to see something and name it as a known, very common divergent series is really very helpful. So we have another new name for this one. This one is called the alternating. Harmonic series. And the only thing that's new about this series compared to the other one is just the alternating portion. If you had to guess, would you say this converges or that it diverges?
Converges.
Turns out it does converge, yeah. So this one does diverge, which is surprising because it diverges very, very slowly, but it's at a cutoff case where things switch from convergent to divergent. This one's surprising because it in fact converges, and it converges decently fast. So what's changing is the alternating portion. So if we were to take a look at this series, we could say that it's also equal to the sum as n goes from 1 to infinity of negative 1 to the n times b sub n, where b sub n is simply 1 over n. So I'm looking at a sequence which would be the harmonic sequence, and the testing is done on just that bn. So that would be the very important thing to do as a step when solving these problems. See what exactly b sub n is in your problem. We're looking for the portion that does not alternate, which is also always positive. So I grabbed the 1 over n and left the negative 1 to the power of n behind. Then we check conditions 1 and 2. First, in condition 1, I have to assert that bn equals 1 over n is decreasing as a sequence. Would you folks agree with that? Yeah, the terms are getting smaller and smaller as n increases, so there's really not much to say here. I would say the sequence, b sub n, as n goes from 1 to infinity, is decreasing. So if it's something that's just really, really obvious, like 1 over n squared plus 1, that thing is decreasing, you could just say it. You don't have to do anything extra. Part 2 says, then take a look at, kind of erased a little bit already on there. It says take a look at the limit as n goes to infinity of b sub n. Some of these steps get kind of confusing because that feels like the test for divergence. But keep in mind, we are absolutely not using, if I find it, it's in there somewhere. We are not using this test at all. But we still have to take the limit. And the limit has to be 0 in particular. But it's also good to keep that in mind that is another test whose steps feel very, very similar. So we go and take the limit as n goes to infinity of b sub n, which is the limit as n goes to infinity of 1 over n, which is 0. And if we did that over here, testing this, that would be a problem because it would have meant the test for divergence fails. But over here in the world of alternating series, this is terrific. If the limit is exactly 0, that's condition 2 on the alternating series test. All that's left to do is state the conclusion. So by parts 1 and 2, we can conclude, therefore, the series as n goes from 1 to infinity, negative 1 to the n divided by n, is convergent by the alternating series test. And then the problem is over. Any questions about it? That's kind of a nice test because there's really work in 3 phases. First phase is to say what the positive portion of the terms are, b sub n. The second portion is to say it decreases or actually show it if it looks a little bit nastier. And the last thing is to look at the limit and state our conclusion. If the limit is 0, we have convergence. If the limit was 4, then, well, the alternating series test has failed, and I would go all the way up to the top on test for divergence. We'll look at some of those other cases next. But what we should do next is, we had a standing assumption that if the divergent harmonic series ever shows up on your paper, whether it's homework or exams, exam 3 or a final exam, if you just assert that's divergent, then that would be just fine. Since it's a common known divergent series, We've proved it diverges in class as well. Same thing holds for this. If this ever comes up, whether it's in a larger problem on homework or exams, if you say it's the convergent alternating series, just throw that in, then you don't have to redo all the work to show it converges. So there's two big series, the harmonic that's known to diverge, and the alternating harmonic, which is known to converge. They show up all the time. So this is two known series that you don't have to test. The rest of them we would have to test, but it's at least good to have two of them that we don't necessarily have to. Any questions about that one so far? Okay, I do have a question myself about this stuff. How do you folks feel about the logic of the test? That the series has to be decreasing in the limit 0, then convergence is guaranteed. Do you folks believe it? Maybe let's do a quick illustration with the last series we looked at, the alternating harmonic series, to see kind of why those two hypotheses are both necessary and sufficient for determining convergence. So what the setup looks like on this particular one is, if we were going to take a look at our alternating harmonic series, we could first expand it and say that this is the summation as n goes from 1 to infinity. It's negative 1 to the power of n divided by n. Or if we were actually to write out all those terms, this converges now, so equals is appropriate. We'd start at 1 to give us a negative 1. Increment to 2 forces us to positive, and we would have a half. Then be minus a third, plus a fourth, minus a fifth, and so on forever. So that's what the terms would look like. If we were to plot the partial sums, we'd start at, say, at negative 1, and we'd be over here. Let's call this negative 1. This will be positive 1, and this will be s sub 1. So s sub 1 is just the first term, negative 1. Then if we go to the next partial sum, s sub 2, that would be negative 1 plus a half. So that would take us to here, roughly. So that's where we would go to on the very next step. So this height, this is 1, 2. This height would be s sub 2. The s with subscript should go on the horizontal axis. So the total sum increases, but as soon as we go to the next one, go down to a third, we're decreasing it by a little bit. But that little bit cannot exceed the 1 over n. So the fact that this is going to 0, and it's also changing the direction. It was at negative 1, it increased to positive 1. Now I'm going to subtract negative 1/3. So the alternating in sign puts me, let's see, 1/3 is about this. So we'd be going to about here for s sub 3. So the limit of that thing going to 0 means we're never actually adding anything too much. Also, because we're alternating, we're sometimes adding, sometimes subtracting, so the heights of those points are converging to something definite. On the next thing, we'll add a quarter. So adding a quarter, that'll bring it back up to about here, maybe. These are getting harder and harder to plot. So this would be about where S5 is for the fifth total sum. As we add more and more terms, it looks like the total sums are converging to a definite actual amount. Any questions about that so far? Okay, so from here all the way to here, adding all of these terms is S5, and the alternating, including the fact that the sequence is decreasing and it's decreasing to the limit of 0, allows a picture like this to work for the partial sums. The partial sums are approaching a definite height, and that means the total series, which is the limit of the partial sums, is converging to something. Something negative, it looks like in this picture. But that's what the alternating harmonic series would look like, and that's the reason for the two portions on the test, that the sequence has to be decreasing and have limit 0. Any questions at all about that? Should we try a harder one, just for the practice? Okay, let's give a harder one a try. So next up, with the same instructions, we're just testing for convergence and divergence. Let's let it be something a little bit more interesting. Let's take a look at the summation as n goes from 1 to infinity of negative 1 to the power of n times 2 times n divided by 4n minus 1. So that's our entire series. And again, probably the very first thing you want to do to this is determine what the b sub n is. It is alternating, so I'd be thinking of the alternating series test, which means we should be able to write it as summation as n goes from 1 to infinity of negative 1 to the n times b sub n, where b sub n is 2n divided by 4n minus 1. So that'd be my very first step. Then looking at the alternating series test, we have to first determine if 2 times n divided by 4n minus 1 is increasing or decreasing. It better be decreasing. This would be something I might do some calculus on to be sure if it's really decreasing, possibly using the first derivative test. But the second condition, part 2, is just looking at the limit. I'd probably do that first. So let's take a look at the limit. As n goes to infinity, I'm doing this first only because it's faster than actually using the first derivative test for increasing, decreasing. So the limit as n goes to infinity of b sub n is the same as the limit as n goes to infinity of 2n divided by 4n minus 1. What would be the value of this limit by inspection?
1/2.
Exactly. So you're always welcome to evaluate these purely by inspection, which works on this one because the powers are both 1. So we took the coefficients 2/4 to get the value of the limit as 1/2. So if the value is 1/2, what does it say about the alternating series test?
Diverging, or it fails, yeah.
It turns out it fails, yes. The alternating series test has just one conclusion, and that's for convergence. I would suspect, however, that if I did not meet one of the conditions, it's possibly because this diverges is the reason. It may not be the reason. It could still converge, but by a different test. So we have to say here, just to remind myself that we have to do something else. The alternating series test failed. Not meaning that the test is flawed, that the proof was flawed and we have to reinvent this in chapter 11. It failed in the sense that we can't draw a conclusion because we didn't meet the hypotheses. Sure, we had an alternating series, but the limit was not 0. But if the alternating series test failed, notice that we took a particular limit, which feels like the test for divergence. Did we take the right limit, though, is the question.
We need to take the limit a sub n.
Exactly. So a sub n is the whole thing. So now we're switching test. The alternating series test cannot be used because we must have a 0 here. 1/2 has caused all the problems for us. But that's okay. We'll take a related limit using the test for divergence. And this is essentially my go-to every single time. If I suspect it's alternating series, but one of the hypotheses, usually the limit, fails, I would always go to the very next step of test for divergence. So the test for divergence says take the limit as n goes to infinity of the entire nth term of the series. So limit as n goes to infinity of negative 1 to the power of n times 2n divided by 4n minus 1. So this is really very interesting because we did do one limit. This limit here is exactly 1/2. Now we're looking at another limit where we're throwing in something to the power of negative 1 at the same time. What would you say should happen to that limit? It's almost like it's heading towards two values. Would you folks agree? One of the values is going to head towards positive 1/2. But then when we get a term that makes it negative, the other strip of the sequence is heading towards negative 1/2. That's really bad. Does that make sense why it's splitting in two different directions? Okay, for convergence of the actual sequence, that's pretty bad because in order for the limit to exist, we have to be approaching one specific number. And that's another reason we need this limit to come out as 0. So this just flat out does not exist. And that's specifically because of this portion right here. we're approaching two different values at the same time. So whenever you have a limit that comes out as a positive quantity, you throw in the -1 to a power n, that limit can no longer exist anymore. That's a nice fact because now for the test for divergence, we've named the test. This is the work, the limit did not exist. The only thing left is the conclusion. Which is that the original series, a sub n, as n goes from 1 to infinity, that would always be referring to the original question, unless specified other words. But this diverges, and we've already named what test we use at the very onset, so that's okay to just leave it there. Any questions about that so far?
So either it has to equal 0 or not to exist or to diverge?
For divergence on this one right here?
Yeah.
In this case, it kind of depends on what you're using. Yeah, if you're using the test for divergence, and this came out to still a half, the conclusion would be the same. Because if we're using the test for divergence, the limit not being 0 means it's divergent. Or does not exist is the second possibility, like you said. That's what happened to us because of the inclusion of -1 to the power of n. So that made it be just a flat out does not exist and nothing else can be said about it. Does that answer your question about that though? Okay. Other questions about this kind of problem so far? Okay, so essentially every problem in this section, when you go to the homework, I think every one of them looks like the alternating series test can be applied because they're all alternating series. However, you'll find that some of them actually do not meet all the requirements of the alternating series test, which means you have to default to a different test. And I would probably check test for divergence on each one of them. Not because it's the only one, it's not the only one that could work, it's just one of the faster ones. Let's try a new problem, unless there's any questions at all so far. Okay, let's take a look at next. Something that should converge, should be nice for the next problem. Let's try this time something that's written in this form. It goes 2/3 minus 2/5 plus 2/7 minus 2/9 plus 2/11. Then just says plus with dot, dot, dot to say that pattern. Well, there's really infinitely many patterns, but the most obvious pattern we see should be the one that continues. So we want to test this for convergence, divergence. And notice that if we did not have the alternating series test, there's possibly not much to do here. Maybe the integral test could work. But because it's alternating positive, negative, the comparison test is out and the limit comparison test is out. So it's a good thing that it at least alternates. And if it looked like this, we make one small design change, let the rest continue with the most obvious pattern, then we cannot test it with the alternating series test. We'd have to make some changes to make that test actually go through. Or, probably better yet, we just need more tests to accommodate stranger things that happen like that with the negative signs. But the first thing I would do on this one is, if we want to test this for convergence, divergence, we need this. So we just need a formula for the nth term of the series. So we can say that this is equal to, for our first step, the summation as n goes from 1 to infinity of, well, we already know it's alternating, so let's throw that in there. Let's put in -1 to the n, and let's check if n is 1, that'd be -1 to the power of 1, which would be negative, but starts out as positive. So we come back here and either go +1 or -1. Now if we insert 1, this would be -1 squared, which would give us a positive term for the very first term. So we're on the right track. Then we're going to say times b sub n, where b sub n is equal to something. So we do need a formula for that positive nth term, b sub n. Once we have that formula, we can actually run the test. But until then, there's not much we can do. So we already have the alternating portion taken care of, so we don't have to mind that when we find the formula for b sub n. Next thing I would look at is, well, I put in a fraction bar because we're dealing with fractions, and the numerators are always 2. So I'll start with that. Then the denominators go 3, 5, 7, just all the odds starting at 3. So if we want all the odds starting at 3, what would you put in for the denominator? Sometimes this is a bit of we sim and roll into the correct answer, so it's good to experiment a bit. Any suggestions for a first try for the denominator? 2n plus 2?
Just n plus two.
Oh, n plus 2, gotcha. With n plus 2, we can check out and say b sub 1 would give us 2 divided by 3, so we're on the right track. And remember, we're going for positive 2/5 because we've already taken care of the negative here. So on b sub 2, we'll have 2 divided by 2 plus 2, so 4, which means we're off on the denominator. But that's good, that's a start. Any change you folks would make to that denominator?
2n plus 4.
If we go with 2n, that's going to help with the fact that we're adding 2 each time. So the 2 and the 2n should go together. The plus 1 is just so that we actually start off at 3. So let's check this out. When we put in 1, it'll be 2 divided by 2 times 1 plus 1, so that's 2/3. When n is 2, that'd be 2 divided by 2 times 2 plus 1, which would be a 2/5. That looks pretty good. So let's try 3. Usually I'm convinced if it works on the third try. So here with 3, we'll get 2, 6 plus 1, so 7. Yeah, I'm convinced. I think we've got the right pattern down. So we have the original terms of that series now in compact form, where b sub n is exactly this. Now we're ready to do the alternating series test. And there's really just 2 parts. First we have to decide, is that decreasing? Would bn as a sequence be decreasing? Yeah, we have something growing without bound to the denominator. The numerator is completely constant, so that's the prototypical form for something that is decreasing. So we can say, then, b sub n is decreasing, and the limit, as n goes off to infinity, of b sub n, it's really just this limit, as n goes to infinity, of 2 divided by 2n plus 1. What would you say the limit for this should be? Yeah, this one comes out exactly as a limit 0. Since we have something constant in the numerator, and the denominator grows without bound. Same reason the sequence was decreasing. So that means conditions 1 and 2 both hold for this series. And there's only one conclusion. If both conditions hold, it must have converged. So let's throw that there. So we can say this series, by this we must be referring to that thing, converges by the alternating series test. So that one's done. Really the major work on this one was really to come up with b sub n. Once you have b sub n, the rest of it kind of just works out. Any questions with that one? Okay, so I think it's also good to remind ourselves at this point that when things converge, they converge to exactly one real number. And sometimes we can find it, but other times we have to settle on an estimate. So that's going to be the second half of this section. We're going to look at how to estimate these types of series when they're alternating. But before we do that, any questions on these problems so far? Okay, so let's discuss the formulas for actually estimating these things. So this is called the alternating series. Estimation theorem. So this is the third of the theorem of this type. If we have a geometric series, for example, we have a formula that says exactly what the total sum must be in case of convergence. It would be this right here, a divided by 1 minus r. So when we have convergence, we can say exactly what it converges to. And that's, again, really, really special. Another thing we looked at very briefly, although it wasn't in the homework, we just looked at it as now a side topic, the integral test also has a procedure to estimate estimating the remainder for something that converges. Now our third one, alternating series test, can also tell us if the series converges by the alternating series test itself, then we can estimate the error or remainder and make an estimate. So those are three cases where, in the first case, we can say the exact sum. In two other cases, we can at least tell you a measure of error in estimation, which is at least something. So let's take a look at our new one. We can say if the alternating series n goes from 1 to infinity of a sub n, which is equal to a1 plus a2 plus a3 all the way up to a sub n plus a sub n plus 1 plus a sub n plus 2 all the way on to forever. So if this thing, much like the one we started with up there, if it converges, then the error in the estimate, that estimate is, we can estimate any series as n goes from 1 to infinity of a sub n using Sn, which just refers to the nth partial sum. So if I want to know the total value of an infinite series, the most brilliant estimation is just stop with finitely many terms, and that's what Sn refers to. So if we want to make that estimate, we have to say how good it is. Then that's what we are referring to by the error in the estimate. That would be all of this. Even though it starts at n plus 1, it is Rn, or the remainder of the series, after estimating with S sub n. Okay, that's a lot of error to say all that. So if the alternating series, so first of all, it has to be alternating. If it converges, then the error here in this estimate is bounded by Rn for the error. We're bounding it, so it can either be a positive error or a negative error, and it's always smaller than Bn plus 1. So that's got to be the best formula ever, because if you think back to what we had to do with the integral test, we had an upper bound and a lower bound at the same time, and those were both definite integrals. However, if we're using the alternating series estimation theorem, then this is a much, much cleaner result. We just use the very next term to make that estimate. Any questions about that? Because the question I would have is, why does that work? Why is that so clean? And maybe a graph will help. So let's take a look at a graph that runs through this entire theorem. So that is the notes that are called alternating series estimate. So you don't have to try to write all this down if you don't write super fast. And this is what a typical question would look like, whether it's a homework question or exam question. This is about how it asks it. It starts off by saying it can be shown the series converges. Use the third partial sum to estimate the total sum of this series. How accurate is the estimate is the final question. So the first question of using the third partial sum to estimate the series, this is about what it would look like as a graph. So here I have the graph of the partial sums. This time they're bar graphs because it just seemed more illustrative. This would be considered S1. If I want to approximate the entire series, this right here by the mouse, oh, hang on, sorry, I moved too high up there. By using just one term, this would be my estimate, about 0.20. The very next term is going to be giving me this as a result of the next estimate. Actually, the estimate of S3 is the result of adding the first three signed areas in the figure below. Oh, so S3 would be this plus this as signed areas. Then every other term is going to be smaller in height. That's just because of the fact that the sequence has to be decreasing if it converges by the alternating series test. So the height of all those rectangulars gets smaller and smaller as we go. So the very next height after this one is always smaller than the very next height after this one is going to be something that's hard to even see with the mouse on the pixel width. And this would be essentially R3. This is going to be the remainder of everything else. So everything else that goes beyond to the right, well, it's going to be above and below, but it's always going to be less than B4, which is this negative height right here. So if I estimate with S3, I have to take this atom together, the assigned heights. The very next one, this height right here, can be no higher than this, and it's the same way all the way down. So the maximum error I can make in adding this to this to this is that entire amount, and that's exactly Bn plus 1, or B4 in this picture. So my error can be no bigger than this. That's a lot of mouse pointers moving left and right. Does that make sense so far? Yeah, go ahead.
Will you ask us to give an error estimation to a certain place?
No, those questions are
Just three?
also always kind of nasty. I would tell you the specific place and just how good the error is. Those are always good questions. Sometimes we want an error within, say, 10 to the power of negative 20 for some reason, and you have to discover the amount of terms for that. But I feel like that's definitely more of a homework problem, and you would have to have a calculator for that kind of stuff. So as the homework problem I asked, or the exact questions, will be more along the lines of what we see here. Other questions so far? Okay, let's give it a try. How about with this one? We could call the part A, show that it converged. Part B, let's actually estimate what it converges to. Because we have to remind ourselves, if this converges, this is now equal to some number, and we'd like to estimate it. So your choice, folks. How many terms should we use to estimate all of this? 3, 4, 5? Let's go for 3. I like that. Let's estimate using 3. That's probably what I would say on the exam, so it's just less writing, which might feel like busy work. So let's call this part A of one large problem. We have a shiny new theorem, and that will be our part B. So this part B now says, estimate the sum as n goes from 1 to infinity of negative 1 to the power of n plus 1 times 2 over 2n plus 1. We might as well cheat a little and just take this because we found a great formula for it. Estimate this using 3 terms. Then determine the maximal error in this approximation or estimation. Let's go with approximation. That should be okay. So that's what a typical problem ought to look like. The first part is really just seeing if we know how to make that estimate. So for the first part, I'd write summation as n goes from 1 to infinity of negative 1 to the power n plus 1 times 2 divided by 2n plus 1 is about equal to, and now we're ready to make the estimate. It's going to be approximately equal to S3. And I used S3 just because it told us to estimate it using 3 terms. That's referring specifically to S3. S is the partial sums, and by formula, S3 would be A1 plus A2 plus A3. So all we have to do is write all that out. And remember, if this was a problem as taken by an exam, if you just tell me what A1, A2, A3 are, then you're free to just stop right there. You don't actually have to do any further computations. So if we wrote this out, for A1, we're just throwing in a subscript of 1. It squares the negative 1, so that's positive. It'll be 2 divided by 3, or we could just take those terms. That'd be a little bit faster. It's this minus 2/5 plus 2/7. So 2/3 minus 2/5 plus 2/7. I forgot we didn't necessarily start there. S3 is just looking at us. If we started here, then just circling it and calling it S3 would have done the job. So we've made an approximation. And if you didn't do any of the fraction work, that would be okay, just leave it like that. Does that make sense so far? Okay, because we're doing it as a homework problem on the chalkboard, let's just see what the number is. sometimes it helps to know what we're looking at, is 2/3, that's like the big box there, minus 2/5, that's like the slightly smaller box, plus 2/7. 2 divided by, if I can punch this in, I get about 0.5523. So this number, whatever it is close to positive 1/2. But then again, if you can't say what your certainty is on any estimate, your estimate is really just about good for nothing. So that's the next part, determine how accurate the 0.5523 really is. Questions so far with that estimate? Okay, so now what we're trying to do is determine how big could this ever get. That's essentially what this last sentence is asking us to do. But by that graph there, which is the generic picture for this situation, a convergent alternating series, we know that nothing can ever be as bigger in height than this height right here. So if we take that, make it positive, then the remainder terms are always bounded between that exact piece. And we can say the following. The error in this estimate is bounded by, or in other words, it can never be larger than the absolute value of R3. This is where it gets a little bit nasty in my head. We call this R3, even though you might call it R4, because it refers to the terms plus 1 later on. We call it R3 because we want these to line up. So that was S3 there. And we still call this R3, even though it involves the term 4 in this case. Well, that's just part of life. There's some issues with our subscripting. So we want to say, there in this estimate is bounded by R3, and this is always less than B4. So that's our estimate. Rn has to be less than Bn plus 1 down below. So that's referring to the 4th square, which would be some negative quantity for us. So it's always less than B4, which is equal to B4. We are going to always have positive. So keep in mind, if you didn't write this out, this has to always be a positive quantity because it's greater than something in absolute value. So we insert 4, we'd have 2 divided by 9. So it can't exceed 2/9. That's not too terrible. Any questions about that so far?
If it does, did we do something wrong?
Yes, definitely. So there's a kind of a finicky way that this could break. And that's a little bit of a extra thing we should put here to be safe. It says, if the alternating series, this one, converges, let's add just a little bit extra, converges by the alternating series test. So if we cannot show convergence by the alternating series test, but it still converges the alternating series, we could possibly have problems over there. But this is, I think, pretty implicit that if we're talking about the alternating series that converges, it should converge by the alternating series test itself. And so that's one way it could possibly go wrong. But if it did converge by the alternating series test, then that estimate has to be solid, unless we made a mistake somewhere else. Other questions about that so far? Okay, so getting this estimate of 2/9, what's essentially telling us is that that 0.5523, let's take a look at it again, 0.5523 plus 2/9, it could be up to possibly 0.7745, and if we do the same operation but minus, on the low end, it could be 0.3300. So if we want to nail that down even further, we just need more and more terms. So we essentially have a confidence interval of where the actual series could lay between, with error 2/9. So if we take this, add 2/9 and subtract 2/9, then it doesn't look as great of an estimate really. That's quite a bit of a range it could take. But any questions about that? Okay, so that's estimating using that theorem. Should we try another just for the practice? How about one more? Does that sound all right? Okay, let's give one more a try.
So when you're writing like errors, like, would you just put it like that, like the errors between those two quantities?
I think that's probably how I would prefer to present my answer, because if I want to give an estimate and then mention the error, I'd like to give the upper and lower limit of where that estimate could lie. What the book is actually going for is just this. So if you stopped
okay.
there by estimating the total magnitude of the error, that'd be okay as well. Other questions about that? Okay, and just as an emphasis, if this was an exam, really this and this is all there is to the answer. There's not a whole lot of work to do. So it's mainly a concept type question when you see it come up. There's another version using the integral test, but that takes a whole lot of steps, and I don't think we assign that for homework. So it's really just has been done for completion. And this is the one you should expect on an exam. Other questions about that so far? Okay, let's try another one. Let's see here. There's so many good ones to do. This one involves logarithms. I think it's been a while since we've dealt with logarithms. If everything goes according to plan, this will be a two-part problem because we cannot estimate the sum of a series if it diverges. So let's say for the first part, determine if the series converges or diverges, and let's let this one be as follows. N goes from 1 to infinity of a sub n is defined to be the total summation as n goes from 1 to infinity of negative 1 to the power of n times the natural log of 1 plus 1 over n. So there it all is. We have some weird stuff going on here, but let's first go through the motions. If I want to determine the convergence or divergence, I would first say because of this, the series alternates. So this is an alternating series with b sub n is just the positive portion. So we can say b sub n in this problem is the natural log of 1 plus 1 over n. So now we have to do two things. We want to determine if the limit of this is 0, and also if this is decreasing. Well, the decreasing is sometimes the hardest thing. Let me check out the limit. Because if the limit fails, then we know we can do some other test, and never have had to worry about increasing, decreasing, which can be a lot more work. So first, let's check out the limit. As n goes to infinity of the natural log of 1 plus 1 over n.
If we want to know if that's decreasing, can we
Yeah.
just look at what's inside of the natural log?
Yeah, that'd be a good way to analyze. We know the graph of the natural log function. If we figure out the limit is some value and that the thing inside is decreasing itself, then that'd be enough logic there to say the whole thing must be decreasing. Other questions about that so far? I like that. We'll do that for our next portion if the limit comes out right, but it's looking pretty good because we do have tricks with limits. The natural log is continuous. The limit of the inside is going to be positive 1. So the natural log is continuous at positive 1 means we can do this amazing step. We can write the natural log of the limit as n goes to infinity of 1 plus 1 over n. And this is by continuity. Continuity allows us to take the limit of what's inside, essentially. So that's always great, because in the limit, 1 plus 1 over n is just 1. The 1 over n would converge to 0 in the limit as n goes to infinity. So use continuity to take the limit of the inside. On the next step, the limit of the inside would just be natural log of 1 plus 0, which means it's the natural logarithm of 1. What's the natural logarithm of 1 itself? Yeah, it comes out as exactly 0. But then we have to go back to which test we're actually using. And this has always been the biggest. Let's look at the flow chart. That looks like a good one. It says if the limit is 0, then that'd be the conclusion for, if that's not the case, divergence. But remember, we don't really care about this because that's the wrong test. So to me, those two tests seem to be mixed up the very most. We should first look at the alternating series test. The alternating series test says, does a(n) equal negative 1 to the n bn, or, so they're asking us, is it alternating, essentially? which is the purpose of all this. The next portion is, yes, if it's alternating. This is the decreasing portion. This is the limit equals 0 portion. So we have the limit is equal to 0. We're on the track to convergence. Whereas the limit being 0 here is good for nothing. They just direct you to the very next test by studying that flow chart. Any questions about that so far? Okay, so we can now say, let's determine if this is decreasing. The limit did come out correctly as 0, which is what we want. Now we can say, also, since 1 plus 1 over n is decreasing, and natural logarithm of x is an increasing function, Bn equals 1 natural log of 1 plus 1 over n is decreasing. That's a lot to put in there. So what I've said so far is this is decreasing. It's decreasing all the way down to 1 as n goes off to infinity. The graph of the natural logarithm function looks like this. It's actually increasing, and we need that. So when we look at the total thing, the natural log of 1 over 1 plus n, as this is getting smaller because n gets bigger, we're going down this way in the logarithm function, which means that in total, the whole thing decreases. Does that make sense so far? That is a way to do it. If you're not happy with that, just hit it with the first derivative, show that the first derivative is always negative beyond some point, say 1, and that'd be another good way to go at it. But because this is an increasing function, the natural log, with something decreasing inside of it, that's always a situation that gives you decreasing overall. With some pictures. I have to always visualize that with pictures, with that kind of argument. So we can now say this converges by the alternating series test. So, n goes from 1 to infinity of a sub n converges. We already said what the test was. We said what the series was, so I'd say that's fine. You don't have to necessarily be redundant and say converges by the alternating series test. If you've told me somewhere somehow it's an alternating series and use the test, then I think that's completely fine. But let's go off to the next bit where we'll now estimate it. Any questions before we give that a try? Okay, so now we know that this is a number, some kind of number. We want to put an estimate down to it. So let's give that a try next, and then we can call it a day. So part B is going to say to estimate the sum using, let's go with 4 terms to make it interesting. Then determine the maximal error in this estimate. Okay, so that's what the problem would look like as an exam question. I might change some of the nouns and verbs a little bit, but that's about what it'll look like. For the first part, I would just write summation as n goes from 1 to infinity of a sub n, which is negative 1 to the n, times the natural log of 1 plus 1 over n. We're estimating with S4. So we just have to write out S4 as A1 plus A2 all the way to A4. Then the last thing to do is just write out what all that stuff is. So starting at index 1, I'd be plugging a 1 here, which starts us off at negative. Plugging a 1 here will be natural log of 2. Then we're going to start alternating. So this is for n is 1. For 2, we're going to get positive. Then it's 1 plus 1/2 in the natural log. And if you left it as 1 plus 1/2, then that'd be just fine. I'll do that just to emphasize. This would be perfectly fine in an exam situation. Practically encouraged so you can get to the more important stuff, the calculus. Then at 3, it's going to be plus natural log of 1 plus 1/3. Then plus natural log of 1 plus 1/4.
We need a minus.
Oh, thank you, forgot we're alternating. So negative, positive, negative, positive. Thank you for that. I would have lost points on that one. It is important that it alternates or none of this stuff works. Any questions so far? Okay, thanks for spotting the negative signs. That always causes havoc. Then we are running low on times ourselves. The last thing to write is that the absolute value of the error is the absolute value of R, we estimate with 4 terms. So I write R4. So the error is the remainder itself. That's just really a definition. The theorem is this. That's less than B5. And as soon as you write down what is exactly B5, we have completed the maximal error estimate. So this is going to be, remember B refers to just the positive stuff, so it cannot possibly be negative, even if we chose B5. So that would be natural log of 1 plus 1/5. Then if we had more time, we could say, well, what is natural log 1 plus 1/5? What does this sum out to? And we could give an interval, just like before, to say the total sum is within those 2 values. But I think this is maybe a decent stopping point. The rest is just calculator punching. It's not completely exciting. Any questions so far with what we've done today? Okay, next class, 11.6, is one of our big sections for sequences and series. We're going to split it over a day and a half. Then 11.7 is really just a review section. So we're going to try to synthesize everything from 11.1 to 11.6 in one day, possibly a day and a half. We'll give it our best try. But if you have questions, feel free to stick around. Office hours starts now.